And if we look at the screen of our oscilloscope, we see we have another signal appearing. Okay, that's from our output. If we look at the frequency here, we have the frequency to be 50 Hz for the output wave. The output wave is on channel 1, and we also have 50 Hz for the input wave. Our transistor has given us an output and the frequency didn't change, but we see that both waves are out of phase. Alright, but frequency remains the same, the waveform remains the same, there's no distortion. Weak signals are easily encountered in electronics, and they are common in systems like microphones, biomedical devices, sensors, radio receivers, and others. They are a problem because they can be susceptible to noise interference from nearby electronics, which can even make them lose vital details. Also, they might be difficult to process or detect by processors and microcontrollers. One sure way to handle weak signals is by amplification. We amplify them, and this we can do accurately with the help of transistors. Simply put, amplification is the process of increasing the amplitude of a signal, boosting the strength of a weak signal to a usable level with high waveform fidelity. By high fidelity, we mean the waveform is preserved, frequency remains unchanged, but we expect our amplitude to increase and our phase might be changed. Before we talk about the terms biasing and quiescent point, let's talk about signals. A signal is a voltage or current varying with time. They can be broadly classified into digital and analog signals. Digital signals are signals for which information is conveyed using only two clear states, on and off, just like we had when we operated the transistor within its saturated and cutoff regions, making it function just as a switch. Digital signals are always either on or off, high or low, 0 or 1. The analog signal can take up any value from a range, so it is considered a continuous signal. A relatable example is turning a knob to get signals into a device for processing. The knob sends different level of data depending on its position per time, and as you continue to turn, it continues sending a continuum. What if it was just a switch or a push button? It can only send two levels, on or off, high or low. Now back to the term biasing. It defines basically how we apply voltage and current to the base of a transistor, setting up its DC operating point or Q point to help it operate properly. So once we are calculating how much current and what voltage should be on our base, we are planning and calculating how best to bias our transistors. The term quiescent point, also called Q point, is defined as the states imposed on the transistor through biasing its base before any signal is applied. Why do we have to bias the base before applying a signal? 1. The NPN doesn't respond to negative base voltage signals relative to the emitter. The PNP doesn't respond to positive base voltage signals relative to the emitter. Let's say we have minus 5 volts at the base with respect to the emitter. The transistor will remain turned off because it requires a positive 0.6 volts with respect to the emitter to be on the base for it to turn on. Next, but we need to send analog signals to the transistor, and they can take up values as is within their range, positive or negative. Also, they can even have peaks lower than 0.6 volts. The transistor will give no response to such inputs. We intend to amplify these signals. If sent to an unbiased transistor, they can force the transistor into saturation or cutoff. So we have this analog signal at the left part of the screen. So if this is our input into the base of the transistor, without it being biased, we would have our output saturate. Once this exceeds 0.6, we would have it saturate, and once it comes down below 0.6 volts, we'll have it cut off. So we're most likely going to have a square wave. But what we desire is to operate the transistor in its active region. That's the only way we can have a high fidelity waveform at our output. So no clipping or distorting of waveform. There are three basic configurations for transistor amplifiers. We have the common collector, the common emitter, and the common base. Here the collector is common or ground for both base and emitter, while the emitter serves as output and base as input. We have the common emitter. In this configuration, the emitter is common or ground for both base and collector, while the base functions as input and the collector as output. We have the common base. In this configuration, the emitter is input, the collector the output, and base the common to both collector and emitter. So let's look at a practical example of how we can amplify an AC signal of 2.5 volts peak to peak, 50 Hz frequency. We are going to be using a power supply of 15 volts and we're hoping to pass a collector current of 1 milliamps using this circuit. First of all, we intend to have a good voltage across VCE. So when our signal comes in, it has a good margin to swing above and below that DC bias. So a good practice is to take VCE to be half VCC. So we have enough room for the signal to swing above VCE and below VCE. So in this case, we are taking our VCE to be half VCC, okay, and that will give us 7.5 volts. Next, we bring in the equation V1 is equal to VRC minus VCE, the voltage across this transistor, this collector and emitter, minus VR2. If we make VRC the subject of formula, we would have V1 minus VCE minus VR2. So we would pick the voltage across VR2 to be 1 volt, so we can have good stability. If we do that, we would have 15 volts, which is V1, minus 7.5 volts, which we have gotten for VCE, minus 1 volt, which is VR2, would give us VRC, which is 6.5 volts. Therefore, RC is VRC divided by IC, where IC is the current through the collector of the transistor, and we have that to be 1 milliamps. So 6.5 volts divided by 1 milliamps would give us 6.5 kilo ohms. But 6.5 kilo ohms isn't readily available, so we have 6.8K available. Using 6.8K as the value for RC, if we calculate backwards, we would see that we would have our VCE to be 8.2 volts. Next, we find the power rating of the resistor we are to use. We have our IC to be 1 milliamps, so if we multiply that by the voltage, 6.8 volts, which is what we will now get if we use 6.8 kilo ohms resistor as RC. That will give us a power rating of 6.8 milliwatts, which is pretty low. So we could use a 1/4 type resistor or any other kind of resistor above that. Next, we find R2. We already have VR2 to be 1 volt. We have IC to be 1 milliamps. So if we divide VRC by 1 IC, we would have 1 kilo ohm. If we find the power rating, IC multiplied by VR2, we would have 1 milliwatt. For this transistor to turn on, we have to have an approximate base voltage of 0.7 volts with respect to the emitter. But in this case, we have 1 volt on our emitter. Remember, VR2 is 1 volt, and that is the voltage across R2. Okay, so we have 1 volt on our emitter. It means that if we have just 0.7 volts here to ground, emitter voltage will be higher than the base voltage, and so we can't have this transistor turn on. So for us to have good enough voltage to turn on this transistor, we have to add 0.7 to 1, 0.7 to what we have here, which is 1.7. So for this transistor to turn on, we would need to have 1.7 volts here. Obviously, this place will now be higher than the emitter by 0.7 volts. In other words, if we have 1.7 volts here, we are actually 0.7 volts up with respect to the emitter. Now, why this is important is that placing a 1.7 volts here gives us room for the swing of our signal when it comes in. So our signal can swing above 1.7 volts and can swing below 1.7 volts and not have the output of the transistor clipping. Next, we find out the current we would need at the base. The current at the base is the current through the collector of the transistor divided by HFE. And from the data sheet, we can see that at 1 milliamps DC and VCE of 10 volts, we have 50 as HFE. And for us, we're working with 1 milliamps through our collector, and we have our voltage above 10 volts. We have our VCE below 10 volts. We're actually working with 8 volts. So it's safe for us to take 50 as our HFE in this case. So next, we bring in the values of IC and HFE, and we get our IB as 20 microamps. IRO1 is equal to IB plus IRO3, where IB is the current through the base and IRO3 is the current through RO3. So IRO1, current through RO1, is equal to I base and IRO3. Next, we have that since IB is 20 microamps, we would allow the current through RO2 to be 200 microamps. And if that's the case, then we can have IRO1 to be 220 microamps by summing IB and IRO3. So we have our RO3 to be VB divided by IRO3, and 1.7 divided by 200 microamps is what it is. And that will give us 8,500 ohms. But what is readily available is 8.2 kilo ohms. So that we would work with. And if we calculate backwards, we'll see with 8.2 kilo ohms, we would have a current of 207 microamps flowing through RO3 instead of 200 microamps, which is still good for stability purposes. Next, we have our RO1 to be VRO1 over IRO1, VRO1 being 15 minus 1.7, and dividing that by IRO1, we have 60.5 kilo ohms. We have 62 kilo ohms readily available, and that we would use. And if we solve backwards, we'll see with 62 kilo ohms, we have IRO1 as 215 microamps instead of 220 microamps. Next, how do we find the value of our capacitors? Okay, so we can use the formula 1 over 2 pi R FC, where FC is our crossover frequency, which is the margin between the frequencies we want to pass and the frequencies we want to block. So using C2 as an example, if we bring in our values, we would have R to be 8.5 ohms, we have R to be 8.2 kilo ohms, and we have frequency to be 50 hertz. We have frequency to be 50 hertz because we don't want any frequency below 50 hertz to go through the capacitor. Another thing, it's a good time to mention that the reason why we have capacitors here is because we don't want DC voltages going through. We need only alternating currents going through this capacitor, and we know that capacitors are very good with blocking DC and allowing AC flow through. So we are putting a capacitor here so every DC signal would not be able to pass through, but whatever signal we have that is analog would be able to go through to the base and can be amplified on this other side. So if we simplify this, we're going to have approximately 0.6 microfarads. So we're going to be using 1 microfarads for C2. We used RO3 for our array here because it's the resistor that is parallel to C2. Okay, so when we're solving for C1, our array is supposed to be the resistance of the load. In this case, we won't be solving for C1 because we're not loading C1 now. It's just us reading to see what signal we're going to get from the output of C1. And we're going to be doing this now practically to see what our result is going to be with an oscilloscope. Okay, so we have our setup here. We have our oscilloscope and we have our power supply. All right, so our oscilloscope has a generator and will generate the AC voltage that we need. So we're working with a wave that is 2.5 volts peak to peak. All right, and that's what we're hoping to amplify. Okay, we have a VRMS of 866 millivolts. Okay, 866 millivolts. We have VPP voltage peak to peak of 2.5 volts. Okay, now that is going into the base of our transistor, and we have our power supply supplying us 15 volts, about 15.4 volts. Okay, and if we look at the screen of our oscilloscope, we see we have another signal appearing. Okay, that's from our output. Okay, so we can see we have the same wave. If we look at the frequency here, we have the frequency to be 50 hertz for the output wave. The output wave is on channel 1, and we also have 50 hertz for the input wave. So we can see the frequency remains the same. Our transistor has given us an output and the frequency didn't change. But if we see that both waves are out of phase. Alright? But frequency remains the same, the waveform remains the same, there's no distortion. Okay, so if we look at our board, alright, we'll see we have electrolytic capacitors. Okay, it's okay to use electrolytic capacitors if the frequency you're working with is not too high. Okay, so but when you're placing your capacitors, you just make sure your positive is on the higher potential while your negative is on the lower one. For this is the output capacitor in my case. You can see the positive pin is on the collector while the negative pin is on my output, because the collector voltage is higher than the, of course there's nothing connected to the output here, so it should be the positive voltage on the higher potential. While for the input capacitor, which is this one, we have the positive on the voltage source coming in, and we have the negative towards the base. Okay, so what if we don't bias our transistor? What if we just send the signal straight to the base of the transistor? What's our output going to look like? Let's try that. So we can see automatically what we have on the screen. This is clipping. Alright, we have a 50 hertz wave and we have a 50 hertz wave, so we can see the frequency remains the same. Alright, but then we have our transistor saturating at this point. Alright, that's not good at all, so we have a distorted waveform. Okay, so you see why biasing is necessary. And this even still looks good because I'm taking my output from the output of the capacitor. If we take our output straight from the collector, alright, we'll see we have a very funny waveform. Now, once we fall back to approximately 0.6, we see we lose our output, and our output cuts off because below 0.6 the transistor shuts off. So you see everything that happened below this part cannot be represented on our output, so we don't have an exact waveform. So this is why we need to bias, so that we can have this swing happening above and beneath our bias. So our bias will be like the middle ground, and this swing can happen above and below.